All right, let's look at polynomial and recognition antiderivatives. If you want to print a guided notes sheet to follow along, you can go to that bit.ly link right there. And before we get into antiderivatives, let's take a quick minute to refresh derivatives. So your power rule for derivatives, and we're going to be using the opposite of the power rule in these antiderivatives. If you have some function that is a times x to the n, f prime is a, you can ignore that constant. You bring the n down times x to the n minus 1, and that's old stuff. Not going to spend much time talking about that, but that is your power rule for derivatives, and we will be looking today at how to do that power rule for derivatives in reverse. And a very common notation when you're dealing with antiderivatives is that if you have a given function that is little f of x, its antiderivative is capital F of x. And we think of that as we kind of make the function bigger. We're going not to a derivative where we reduce powers, we're adding powers, and we'll have an antiderivative that is a bigger function, so to speak. So we'll call it capital F of x. That also means that the derivative of capital F is little f. And we're just going to feel our way through these three problems and see if we can come up with functions that would give us that for a derivative. And this first one, my antiderivative, which is capital F of x, I'm trying to think of what gives me a derivative of 4x cubed. And I tried to make these first two so you can pretty easily see it. And the derivative of x to the fourth is indeed 4x cubed. The derivative of x squared is 2x. The derivative of 7x is 7. So the antiderivative of 4x cubed minus 2x plus 7 is that, except I could put a plus 4. And the derivative of that capital F is still this little f. I could put plus a 9, 98, pi. I could put any constant here, and the derivative of that constant would be 0, still preserving the fact that this little f is the derivative of that capital F. And what we do in the world of general antiderivatives is when we find the antiderivative, we will put a plus c at the end, just to indicate that there could be some constant added to that antiderivative and it would still be correct. And so we need to remember plus c for all general antiderivatives. And so let's look at number 2. This one is the recognition category. This is not a polynomial like number 1 was. And so for this one, when you see 1 over x, you really should get to where you just recognize that the numerator is the derivative of the denominator, and that sounds an awful lot like a natural log. So it's the natural log of x, and secant squared x, you should just recognize that as the derivative of tangent x. There is no process for that. You just need to remember your derivatives, your trig derivatives, and you need to know that 1 over x is the derivative of natural log of x. And I'll spare you the time right now, but I want to let you know that anytime you do an antiderivative and you have natural log of something, get in the habit of putting that argument in absolute values. For now, I'm just going to ask you just trust me. A short explanation is it's a domain preservation thing for the original little f to its antiderivative capital F. You want the domains of both to be the same if possible, and we can make it the same by putting that x in absolute values. With my students, I'll talk about that in more detail later, but just know that when you do an antiderivative, if a natural log shows up, go ahead and put the argument in absolute values. It will not be wrong, but it can be wrong if you do not include the absolute values. So let's look on to the last one. And this one's a little bit trickier for that first piece. So we have some antiderivative, and we have x cubed, and we're trying to think of what function would give me a derivative of x cubed. And I know if my derivative has x cubed, my original function should have started with an x to the fourth. So when I subtract 1 from that exponent, it does give me the x cubed that I want. However, a quick check, the derivative of x to the fourth would actually be 4x cubed, not 1x cubed. And the way we can fix that is just by putting a coefficient of 1/4 in front of that x to the fourth. Now when you differentiate that, you do get the x cubed that we want. E to the x, as far as I know, is the only non-zero function that is its own derivative, and it is its own antiderivative as well. And then don't forget the plus c. And so there are a few antiderivative problems where I didn't even teach you any kind of method or formula for finding an antiderivative. We just kind of felt our way through those. We're trying to come up with some function that produces these given functions as derivatives. And now the formula for that makes it a little bit easier If it is in polynomial form, if your little f is something that is in a form that resembles a polynomial, that'll be a number times x to a number power, then the antiderivative follows this pattern. And just like with derivatives, we can ignore that constant a. If there's a constant times your function, that does not impact the antiderivative. And what I need to do first is we'll do the power rule for derivatives in exact reverse, where for the power rule, we finish by subtracting 1 from the previous exponent. So for antiderivatives, we will start by adding 1, and then we will always divide by that new exponent. And so think about the power rule for derivatives. We multiply by the previous exponent and then subtract. We're going to do that in the exact opposite order. We will add, and then we will divide by the new exponent. And that is the same thing as, if you want to, you could write it as 1 over n plus 1 times x to the n plus 1. And that's kind of how I did it with that 1/4 x to the 4th on that previous example. And so with that in mind, let's look at a few examples. And I want to, if possible, I want to see my functions written as something times x to a number power, just like when we first learned how to do derivatives. And I don't like the square root. I'm going to change that square root. X to the 7th is fine. I'm not going to change that. But the square root of x, let's change that to x to the 1/2. That way I can see a number exponent that I can add 1 to and then divide by the new. And so when I do this antiderivative, capital F of x, I add 1 to the previous exponent, so 7 plus 1 is 8. We will divide by that new exponent, and then I will repeat that for x to the 1/2. 1/2 plus 1 is 3/2, and we will divide by 3/2, or at least that's how I prefer to do it. Some people like to write 1/8 times x to the 8th, but I just prefer to put my x to the 8th over the 8. Doesn't really matter. And then don't forget there is always some unknown plus c when you're doing a general antiderivative. And if you want to, you can rewrite this, like I said, as 1/8 x to the 8th. Not a whole lot of change there. However, 1 over 3/2 is the same thing as 2/3 x to the 3/2. And that plus c just kind of comes along for the right. No need to write it that way unless it's multiple choice and you want to match your written work with the options. Let's look at number 5. And just like with derivatives, I always tell my students before we just dive into antiderivatives, always try to think of ways algebraically you can make the calculus easier. And right now we have a product. So just like there is a product rule for derivatives, there is a product rule for antiderivatives. We call it integration by parts. However, the product rule for antiderivatives, where we unpack a product, is quite cumbersome. And if at all possible, you will absolutely want to avoid doing the product rule in reverse. And in this case, we can very easily avoid that by simply expanding this. We have two binomials. I'll multiply them out. That's going to be this. And in doing that, I now have turned this into a polynomial where we can follow that power rule for antiderivatives. We will add 1 to the previous exponent and divide by the newly generated exponent. And if you have a constant in front, that 5, it's not really helping me because I know I need to add 1 to 3 and divide by the new exponent. I'm just going to leave that 5 there. I'm going to make it 5 times x to the 4th over 4. And we can do that for all of these that have a coefficient. I can ignore that 3, and then the antiderivative of x squared, we add 1. 2 plus 1 is 3. Divide by the new exponent. Same thing for this one. This is 5x to the 1th. And so I'll just ignore the 5, and that'll be x squared over 2. And then 1 would be the derivative of x. So the antiderivative of 1 is x. And then a plus c. And then if you want to clean this up a little bit, that is the same thing as 5/4 x to the 4th minus the 3's divide out, just x cubed, and 5/2 x squared plus x plus c. And then we can leave our answer like that. You can leave your answer in that second line right here if you want. And that is my antiderivative. By the way, if you want to, you also can skip straight through to that final one, and hopefully very soon we will be comfortable enough with the power rule that we can just spit out the polished, more aesthetically pleasing answer. Let's see, go on to Oh, that was it. So those were the two examples there. I swear I had more, did I not? Hang on a second. Let me pause this. All right, here we go. I thought I was missing some. So yeah, so here are a couple more examples, finding general antiderivatives. And again, you want to see these, excuse me here, you want to see these as a number times x to a number power, if possible. Sometimes that's not very convenient. However, this one, 2 over x to the fourth, 2 over x to the fourth, I can rewrite that as 2x to the negative 4, and 1 over x squared plus 1. In a perfect world where students never forget anything they ever learn, you recognize that as the derivative of inverse tangent x. I don't want to change the way that looks because I like it as it is. And so now my antiderivative, cap f of x. Again, I'm going to ignore the 2. That 2 is not really helping me in any way. Negative 4 plus 1 is negative 3. I will divide by that new exponent. And then 1 over x squared plus 1, you should just recognize that that is the derivative of inverse tangent x. And so there is your antiderivative in its unsimplified form. If this were a multiple choice question, they likely would move that x cubed back to the bottom, make that 3x cubed in the denominator. Inverse tangent, you can't really change the way that's written unless you want to write it as arctangent x. There we go. Let's see number 7 here. Again, it's kind of ugly. I want to clean this up some, and we can indeed clean this up. You can bring that x squared up, make that x to the negative 2 times x cubed minus 4x plus 5. And when you distribute that x to the negative 2, we end up having a function that is x to the first minus 4x. Negative 2 plus 1 is negative 1, and then 5x to the negative 2. And we run into a little bit of a situation here, because if you dive straight into antiderivatives without really thinking about what you're doing, we're going to add 1 to this exponent, make that x to the 1 plus 1, that's 2, divided by 2, that's fine. And then I have 4, I'm just going to ignore the 4. And the antiderivative of x to the negative 1, if you try applying the power rule, you end up with negative 1 plus 1, which is 0. Nothing wrong with x to the 0. However, there is a major problem with dividing by that mu exponent. Cannot divide by a 0. So that's not right. By the way, just peeking ahead, I'm going to erase this in a second. X to the negative 2, no problem there. Negative 2 plus 1 is negative 1. Divide by the mu exponent. And that's okay also. A little bit ugly, but it's fine. It's fine to have the x to the negative 1 over negative 1. X to the 0 over 0 is a huge problem, and we don't want to do that. And so what I'm going to do is, actually, I'm just going to erase all of this. I'm going to change the way 4x to the negative 1 is written, because that is the only time where we don't want x to a negative exponent. Any other negative exponent in the world of power rule antiderivatives is fine. An exponent of negative 1 will always give you that divide by 0 situation. And so I'm going to rewrite that as 4 times 1 over x, because if I write it that way, I now see the 1 over x, which I recognize as the derivative of the natural log of x. So I'm going to apply the power rule now. The antiderivative of x is x squared over 2 minus 4 times the antiderivative of 1 over x. That's your natural log situation. And don't forget the absolute values to preserve the domain of the original little f, plus 5 times negative 2 plus 1 is negative 1 over negative 1, divided by that mu exponent, and then put plus c. And for this one, I'm not going to simplify that any. You can make this negative 5 over x if you want. And I'm going to go on and add a few more notes, and I probably won't finish every example on this sheet, but we'll look at a few more. So another type of notation we can use, instead of using the little f, capital F notation when we're dealing with antiderivatives, there is something called an indefinite integral, and some of you may know what a definite integral is, some of you may not. I'm going to explain the difference in a minute. But an indefinite integral is an integral, that's the little squiggle s thing that does not have the limits of integration. And if you ever see this thing right here, where we have the squiggle s and f of x and a dx, what that is asking you to do is find the general antiderivative of the function little f. So it's the same thing, same type question, just a slightly different notation, and then just a very quick explanation of a definite integral. This is not part of that sheet that I mentioned earlier if you chose to print that or if I gave you a hard copy. This is a definite integral, and these are the ones that refer to the area under a curve or area between the curve f of x and the x-axis. And in this case, a and b are called the limits of integration. And the f of x dx is called your integrand, but I basically wanted to point out the limits of integration because that's the part that we're missing in the general antiderivative. If you have the limits of integration, we do something different, and we'll talk about that some other time. But let's look at a few of these examples that are in this indefinite integral notation. And so right here, it's just like this is my little f of x, and I want to find the antiderivative of that. And just like before, if I have a radical, I don't really like the radical notation, and so I'm going to change this. 6x squared is fine. I don't need to change 6x squared. However, the cube root of x is the same thing as x to the 1/3. And notice that I am keeping my squiggle s and my dx because I have not yet found the antiderivative. All I did is a tiny little bit of algebra properties with radicals. Now that I'm about to add 1 and divide by the new exponents, we will have our answer. And so the antiderivative is 6, and I'm going to carry the 6 with me. 2 plus 1 is 3, and we will divide by that new exponent of 3. X to the 1/3 plus 1. 1/3 plus 1 is 4/3, and we will divide by 4/3. And we always want to put a plus c, and this one does clean up to 2x cubed plus, and if you divide by 4/3, that's the same as multiplying by 3/4. X to the 4/3 power plus a c. Number 9 is about as easy as they come. That 7 is a constant times the function does not impact the antiderivative, and so the antiderivative of e to the x is e to the x. That 7 is just going to come along for the ride. Put a plus c, that's kind of nice. That's about as easy as an antiderivative can be. And there are 2 more examples, and I think I'm going to skip number 10 here. To do number 10, you would start by distributing. There is, as I said earlier, a product rule in reverse called integration by parts, but it's really a booger. And so for number 10, you would actually distribute first, make that 6x to the 6th plus 4x to the 5th. And the gods of math would prefer you to put that integrand in parentheses. But I want to skip to number 11 because number 11 kind of has that inverse tangent. Look, I see x squared plus a number in the denominator, and I know inverse tangent's derivative is 1 over x squared plus 1, but inverse tangent doesn't have a 2x or an x at all in its numerator outside of chain rule applications. And so this is one. Technically, it's called U substitution, and we'll talk about that in my class later, but I do consider this recognition because I'm looking at this fraction. If I ever see a fraction in the world of antiderivatives, I will test this first because I see a fraction and the numerator is the exact derivative of the denominator, which is how we have always done the derivative of a natural log function. So the derivative of the natural log of f of x is f prime over f, and that's just something you should know from chain rule and from logarithmic derivatives. And so when I see a fraction, if I see that the top is the derivative of the bottom, that tells me this is the end result, this is the derivative of a natural log function. And so this one, there is no process, it's recognition, it's the natural log of absolute value, x squared plus 7, and in this particular instance, the absolute value isn't necessary because x squared plus 7 cannot be negative anyway. So if you forgot the absolute values on this case, it's not wrong, but it's never wrong to put absolute values there. I say always use the absolute values and not try to worry about whether it's needed or not. And that is a good stopping point on this one, and hopefully this makes sense.